Hello, everyone. My name is Sean Name, and today we'll be doing our fluid mechanics project 2 simulation of an airflow over a flat plate, part C, where I find the skin friction coefficient and the wall shear stress. So first things first, we're going to click here on geometry and make sure that our analysis type is set to 2D. And we're going to right click geometry and new design modular geometry, and that will open up a new window where we can start our sketching. Once you start opening this up, I'm going to go a little bit, press the Z plane, and then we're going to be in the XY plane. And we are going to sketch a rectangle about the origin. So make sure your cursor is lined up with the origin, which I don't think mine was. Let's try that again. There we go. And then we want to do some dimensions. So then we'll do our horizontal dimension. So click this vertice, go up. And this is going to be set as in the product to 1 meter. So you see 1 meter, and our unit is in meters, so that's all good. We'll set our vertical dimensions by clicking this vertice and this vertice, and we'll just set that to 10 centimeters or 0.1 meters. That was something is not right here. I'm sorry, let me go back to our horizontal. Yeah, here. Here, this should be 1 meter, and this should be the 0.1 meters. So H1 is 1 meter, V2, which is our vertical, is 0.1 meters or 10 centimeters. So once we have that, we go to concept and then surface from sketches. And then we can go click on the XY plane and click sketch 1, and then click apply and generate. So that will generate us this little highlighted square, and this is all we need to do for our design modular geometry. Exit out of here, and just for good measure, click update, and then that should be all good to go right there. Next step, we are going to open our mesh, and no more settings need to change in there. So I'm just going to double click on mesh and let that open up. Okay, so now that our mesh has opened, we're gonna right click on to mesh, insert, and we're just gonna start off. Actually, make sure that this is selected. So let's make this next step easier. We're gonna insert a face meshing and just click right here. We've just selected that, and this will allow us to. I want to make sure that our geometry is correct. Yes. Apply, and then we click generate. And then when you click on the mesh, you just see some squares, which is not what we want right now, but we are going to continue to add some more sizing meshes. So here on, now we're going to do a edge. So we just easily select these edges. And then, so our geometry is correct. We want our typed to be a number of divisions. And then I believe we should do actually, yeah, 50 divisions. Actually, it'll be easier if we delete this, yes, and then let's go mesh, insert a new sizing, and control click these two, click apply, and instead of by element size, we'll do number of divisions. And then this will allow for a finer resolution of our mesh. And we'll do 50 numbers of division here. And then our capture curvature will be set to no, and then our behavior will be hard, so that Fluent only doesn't pay attention to any other behaviors. And then that should be everything for those two edges. We don't need any bias here. That'll be for the next one. So then we can press generate again. And this is going to add more little squares, but you have a little slanted everything. So not quite done yet. So we're going to do another mesh sizing, make sure we still have edge selected. So then we can select this outer edge and click apply. Again, type will be number of divisions and growth rate, I'm sorry, capture curvature is going to be set to no. Behavior is hard. And we do want this bias right here. And then also almost forgot 60 divisions right here. Our bias factor let me see. We'll do a 70 for our bias factor. All right, yep, and that's looking good. As you can see, it's getting slightly bigger as it goes up. And then that should be good for that certain mesh. And then we click generate again, and then we're gonna get this weird thing going on the edge there, but this is what we want. It's gonna end up coming together very well. So it's gonna insert another sizing on the other side here. And it's gonna be a very similar process. So let's click apply. And again, not by element size, but by number of divisions to be 60. Growth rate, normal, capture curvature will be set to no. And then bias type, yes, we do want to have this bias right here. Bias factor, again, will be 70. And then I want to click on this again and click reverse bias. So now it should be looking the same as the other side has it. It's really tiny at the bottom, going straight up. One edge, yes, yes. Growth behavior, almost forgot. It needs to be hard. Awesome, number of divisions, bias factors, looks all good. Mesh, and I'm going to click generate once more. And that is a much better looking mesh. Let's see. Make sure all of these meshes, 60. These should all be good. And then one thing we want to do is actually, so we have edge selection on, and we do want to name these what am I trying to say here? And we're gonna name our selection. So we'll call the bottom one plate. This one we click N, and this will be inlet. Click this edge, click N, and this will be outlet. And then this top one, and again, this will be far field. Awesome. Update. Okay. Click out of here and then click update. And it's awesome. And then now you're going to double click setup. That might take a second. Oh, I actually did it. So we're going to double precision, solver process set to 2, and click start. So that's going to take a second to load on the other side. Okay, and now we're waiting for all this to load up. All right, just give it one more second and everything should be coming in here shortly. All right, awesome. This is what we do like to see. We have our arrows going in, our arrows coming out. Our mesh looks awesome. So for setup, all this looks good. All right, so now we're gonna get started by switching. Let's go models. We are not in viscous flow, so let's change this to laminar flow. I click OK. Make sure that applies right there. Materials, fluid, air. We're gonna go up here. Our density is gonna be 1.2, And our viscosity is given as 1.8 e to negative 0.5. And let's change and create. And that looks all good. Click close. So now we have that all done. And let me make sure this time set steady, pressure based. And then one also good thing to change is your residuals. So where can we find that? And we're going to have to change our boundary conditions as well. So actually let's go inlet. And I like it rather from this screen. And velocity inlet is going to be 2 meters per second. Click apply and close. And yes. And then for boundary conditions, you double click this, click inlet, double click here. You see that also. So click apply and close. That all looks good. And then for our plate, want to make sure this is the just give this a second. Plate should be a stationary wall with no slip, so we can just close that. In this far field, so we want to change this to a type symmetry and press apply. Close. And then for solutions, let me find that. Solutions, double click on methods, and then we're just going to do a simple solution today. And the rest of that looks good. And then under initialization, just going to do standard initialization. And we want to compute from the inlet as our reference. And then this should be 0 meters per second. But the x velocity that we carried over did carry over when we set up our boundary conditions, which is all good. And then one other thing I would want to change is our residuals, as I was saying earlier. So here I'm just going to add 2 zeros to everything, just make everything a little bit more precise. And you just click OK, and then that will save once we do our results. And then now we are ready to initialize. So we click initialize. You might get a little pop-up. It might be scary, but we'll proceed with it. So I'll make sure this still says inlet. 0. Yes. Initialize. Click OK. And then now after that, run calculation. And then 10,000 iterations. And then calculate. And then this is going to bring us some charts that are going to flow. So they should end up converging. This is not for my part of the experiment, but this is still very nice, very helpful. And yep, this is going to just keep going. So let's say calculation complete. You can just switch over your tab if you want to see that. And then now for the next part, we are going to hop on over to creating our 2 charts, one for the wall skin stress and one for the wall skin stress and the shear stress and coefficient of friction. Yes. So plots XY plot. So X plot, Y plot 1 is we are going to keep this onto wall fluxes. And first one we're going to want is wall shear stress. So wall shear stress from the plate, keep this here, order points, and then use save/plot. And yeah, if I was doing it, let's make sure we are only the plate is selected here, so not the outlet, just the plate. And save/plot. Yes, so that should, yeah, that looks much better. And now you have your wall shear stress here, but we do want to write to file so we can actually see this. So you're just gonna save this to whatever location you want, and I'll pull it up on my end because I already saved this. And then to do the wall skin stress, you can keep it on wall fluxes, but then you're gonna go down here to wall shear stress. If go to shear stress coefficient, I can click it, yep. And we're gonna undo write to file just so we could make sure that this plots correctly and that looks good. Then you write to file, write, and then you're gonna save it to whatever location you want. So now once you've done that, you're gonna open up your open up my Excel sheet as well as what was outputted. So here is the Excel sheet that I have made today, but let me just show you the raw data that will, so it's gonna ask you just on Notepad, you are just going to copy this data into your Excel sheet into a table. So this is skin friction coefficient. And then, okay, here we could also see our shear stress. And yeah, so you copy all this data into Excel, and then you're going to get something that looks something like this. So I've just made it into a table, made some charts. So for a distance along the plate, our skin friction fluent. So these are both simulations. These are just straight copy pasted. But you only have to paste this one time, so these don't change. And this is your from your simulations, your wall shear stress, and your skin friction, and your Reynolds number, skin friction, and wall shear stress. You could all calculate using Excel formulas here, which I have done, and then that populates it all the way down for all your iterations. And then the fluence here, if I click on this, you can see which values are being plotted here. So we have the distance along the plate, and then comparing that with the wall shear stress fluence, and then distance against plate against wall shear stress theoretical, and this is the comparison of the two. And you can see after the distance along the plate, it converts to the same value. Same thing here goes for fluent versus theoretical. And again, I click on these and you can see which data they're pulling from. Just for an example, all you would do is just go down, select this. This is for the wall shear stress. Select this as well. I'm holding control, by the way, and select your theoretical. And you just go to insert, just recommended charts, all charts. Do a line chart, and then yeah, you'll be inserting this chart, and then you'll get the same thing. Vice versa, you'll do for same thing for skin friction. You are going to want to go boom, and then you can go just skin friction theoretical, skin friction fluent, and then yes, your distance. Insert recommended charts, all charts, line, and then let me make sure I get the right ones here. It's because I chose the yeah, I see the problem. Sorry about that. So for skin friction, put down, and skin friction theoretical, all the way down. Insert recommended charts. Yep, see that works now. Line chart, and you'll be inserting this one. And then you'll get your fluent versus theoretical skin friction and your fluent versus theoretical wall shear stress, both plotted with the distance along the plate as your x-axis and your wall shear stress or your skin friction coefficient on the y-axis. And that will complete your project, and then you can go ahead and put these into your file, and all will be good to go. So thank you for watching this video. I hope you guys will enjoy it and watch this a couple years later and regret that I took this class. I'm just kidding. It's a lovely class. Thank you, Dr. Osbey.